We now learn about inverse functions. Say we have a function f of x for which we'll consider the input values we see here. Then f of x will map these input values onto a set of output values. And for the sake of this example, I'll go ahead and say that the function f of x is f of x which equals to 2x plus 6. Now what we see here is a mapping diagram, and we've seen these before. And so through the function f of x, each of these input values will be mapped on to its respective output value. So for instance, for the input value -2, it will be mapped onto the output value 2. Indeed, 2 times -2 plus 6 would give us 2. And as we already know, to obtain the set of output values, all we need to do is replace the x we see inside f of x by each of these input values. And by all means check, but for the input value 0, we'd get the output 6. For the input value 1, we'd get the output 8. And for the input value 4, we'd get the output value 14. Okay, now a function's inverse function is the function which maps the numbers inside this output box back onto the numbers inside the input box. So this function's inverse function is a function such that when we replace the x inside it by 14, we'll obtain 4. When we replace the x by 8, we'll obtain 1. When we replace the x by 6, we'll get 0. And of course, when we replace the x by 2, we should obtain -2. So the function that does that is this function's inverse function. And the notation we use to refer to a function's inverse function looks like this. F with a sort of superscript, -1 of x. Now careful, this -1, which looks a bit like a power of -1, is merely there for notation. And that's important to keep in mind. Because when referring to a function's inverse function, the notation f to -1 of x does not equal to 1 over f of x. Indeed, that's a trap you don't want to fall into, since when working with numbers and exponents, we'll have seen that 3 to the -1, for example, is equal to 1 over 3. But when it comes to functions, this -1 here is referring to the inverse function. It's not a power. So do keep that in mind. Okay, now that that's out of the way, given a function like this one, how do we find an expression for its inverse function? Let's see, and I'll go ahead and write expression for inverse f of x. To find a function's inverse, we can follow 2 steps. And we'll write down those 2 steps for the function we have here. And here they are. Step 1, we're going to swap the x and y in the expression y equals to f of x. And so I'll quickly write that. I'll say swap x and y. Now here's what I mean. Copying this function f of x equals to 2x plus 6, but instead of f of x we'll write y, this function would look like this. Y equals to 2x plus 6. And so all this first step is telling us to do is to copy this again, but we'll replace the y by x and the x by y, which would look like this. X equals to 2y plus 6. And that's the first step done. So we move on to step 2. And in step 2, we need to rearrange the expression we just wrote in order to make y the subject. And so here I'll just write make y the subject. Okay, well starting from the expression we had there, x equals to 2y plus 6, and in fact looking at this we'll carry on with the working at the top of the page here, like so, and I'll even copy that again, x equals to 2y plus 6. To make y the subject, the first thing I'll do here is get rid of this 6 that's being added on the right hand side. And so for that I'll subtract 6 from both sides, so we'll have x minus 6 on the left hand side. Let me just write that. We'll have x minus 6, which equals to 2y plus 6 minus 6, which is just 2y. The next thing I'll do is get rid of this 2 that's multiplying the y on the right hand side, and to do that all we have to do is divide both sides by 2. And so we quickly end up with x minus 6 over 2 equals to 2y divided by 2, which is just y. And of course we can rewrite that as y equals to x minus 6 over 2. And as such, we're done. this function y equals to x minus 6 over 2 is this function's inverse function. And we could write our final answer as inverse f of x equals to x minus 6 over 2. And I'll go ahead and box that result. There we go. Okay, now just as I said at the beginning, this inverse function should map each of these output values back onto its respective input value. And so for the sake of convincing ourselves that it does, let's see what inverse f of 8 gives us. Well, according to what we said earlier on, if we replace x by 8 in our inverse function, we should be getting 1. So let's quickly check that. If we calculate inverse f of 8, that would equal to 8 minus 6 over 2, which is equal to 2 over 2. In other words, inverse f of 8 is equal to 1, which is definitely the corresponding input value we had earlier on. So I'll put a little tick mark here. Another example, we could check what inverse f of 14 is. And again, in theory, if we replace x by 14, we should be getting 4. So let's see if we calculate inverse f of 14, that will equal to 14 minus 6 over 2, which is equal to 8 over 2. In other words, inverse f of 14 is equal to 4, which definitely corresponds to the input value we had earlier on, and so clearly this inverse function works. Okay, so now that we have an idea of what an inverse function is, as well as how to find an expression for a function's inverse function, what about its graph? Well, let's see, on an xy grid, I'll go ahead and draw, or I should say sketch, the function f of x which equals to 2x plus 6, and then we'll see how we can sketch that function's inverse. So let's see if I draw a very generic xy grid here, something looking like this. That's my x-axis, and that's my y-axis. There we go. And now let's go ahead and draw y equals to f of x, in other words, y equals to 2x plus 6. Well, y equals to 2x plus 6 is a straight line graph, and it crosses the y-axis at 6, and you can go ahead and check, but it will cross the x-axis at negative 3. And so let's see, I'll say that 6 is right there, and I'll say negative 3 is right there. So y equals to f of x is a straight line graph that I'm drawing right now. There we go. That's y equals to f of x. Now I should say, if you're unsure of how I find this negative 3 here, let me quickly remind you that if we have y equals to 2x plus 6, the value of y at which it crosses the y-axis is given to us by the 6 we see here, and to find where it crosses the x-axis, we'd replace the y on the left-hand side by 0 and solve for x. And in doing so, you should quickly find that x equals to negative 3. That being said, I carry on. An important fact about a function and its inverse function is that they are the mirror images of each other across the line y equals to x. And that's a very important rule to remember. So I'll say it again in just a minute. First of all though, let me draw or sketch the line y equals to x. That's the line that passes through the origin whose gradient, or slope, is equal to 1. And it would look something like this. There we go, that's y equals to x. I'll say it again, given a graph of a function y equals to f of x, if it has an inverse function, then its graph is the reflection of the graph of f of x across the line y equals to x. So the graph y equals to inverse f of x should be the reflection of this orange line here. So you could probably guess that line will follow what I'm hovering over right now. But alongside that rule, there's another important fact which is definitely worth keeping in mind. Going back to the mapping diagram we have here, for any input value a, f of x will map that input value onto an output value which I'll call b. And consequently, the inverse function will map b back onto a. And as simple as that may sound, that actually highlights a very important fact, which I'll write over here. And here's the idea. If y equals to f of x passes through a point a, b, so that's a point with x-coordinate a and y-coordinate b, then the inverse function y equals to inverse f of x will pass through, and I'll just say passes through, the point whose coordinates are swapped, so b a. And let me just box that before I show you how useful this result is when we're asked to sketch a function's inverse function. Here it is. For y equals to f of x, we can see from our sketch here that it passes through these 2 points, namely the x-intercept and the y-intercept. Now the x-intercept has coordinates -3, 0. And what this rule tells us is that the inverse function will therefore pass through the point 0, -3, which would be right here on the y-axis. Similarly, the graph y equals to f of x passes through this point right here, whose coordinates are 0, 6. And consequently, thanks to this rule, we can state that inverse f of x has to pass through the point with coordinates 6, 0, which would be right here on the x-axis. And now thanks to these 2 points, we can draw this function's inverse function. Indeed, it would be the straight line graph passing through those 2 points, which would look something like this. There we go. That's y equals to inverse f of x. Now, although I haven't drawn this to scale, hopefully you can appreciate that the graph y equals to f of x and the graph y equals to inverse f of x are mirror images of each other across the line y equals to x. And that will always be the case. Furthermore, thanks to this rule here, we quickly notice that, as such, the x-intercept of f of x becomes the y-intercept of inverse f of x, and the y-intercept of f of x turns into the x-intercept of inverse f of x. And in this particular example, we can also point out that f of x and inverse f of x intersect at a point. And that point is right here. And the key thing to realize here is that that point lies on the line y equals to x. Again, that will always be the case. If a function and its inverse intersect, then that point of intersection must lie on the line y equals to x. It's also worth mentioning that if a function f of x crosses the line y equals to x, then the inverse function must also cross that line at the same point. There we go. That's how we can graph or sketch, and I'll just say graph, of inverse f of x. Okay, before I finish this video speaking of the domain and range of a function and its inverse, let me quickly point out that in this particular example, f of x was a straight line graph. In other words, f of x was a linear function. And so to sketch both f of x and its inverse, we only really needed 2 points for each of them. But if ever we had a more complicated function, we may like to have more points to guide us for our sketch. In which case, all we'd have to do is remember the rule that we boxed here, and use any point we could possibly find on the graph of y equals to f of x. And so for the sake of illustrating that, let's say we were to consider one more point on the graph of y equals to f of x, such as the point with coordinates -2, 2, which would be roughly here. That's the point with coordinates -2, 2. Then thanks to this rule, we could state that inverse f of x has to pass through the point with coordinates 2, -2, which would be right here. And if ever we're not given enough coordinates of y equals to f of x, just remember you can always sketch y equals to inverse f of x using the fact that they are mirror images of each other across y equals to x. All that being said, let's move on from the graph of inverse f of x to finish this video speaking of the domain and range of inverse f of x. So I'll just say domain and range of inverse f of x. There we go. Given a function f of x and its inverse function inverse f of x, we've seen that their input and output values are effectively swapped. Indeed, we've seen that for a function f of x, if for a given input value a we get an output value b, then for its inverse function, if the input value is b, then the output value is a. So the input and output values are indeed swapped. And that statement can be generalized for the domain and range of a function and its inverse. And we can summarize it in 2 bullet points. Here it is. The domain of inverse f of x will equal to the range of f of x. And so this is effectively telling us that the input values of the inverse function are equal to the output values of the original function, and the range of the inverse function, so range of inverse f of x, is equal to the domain of f of x. And in turn, this is effectively telling us that the output values of the inverse function are equal to the input values of the original function. And so essentially, this is just confirming what we had already seen, but we're saying things in a slightly more formal way. And let me insist, this rule is very important, so do make a note of it. In fact, let me quickly finish this video by giving you an example of how this rule may be used in an exam question. Let's say we're given a function f of x, which is equal to the square root of x minus 4, so square root of x minus 4 plus 1. And we're told that this function is defined for x is greater than or equal to 4, and we could be either told or previously asked to find its range, which would be y greater than or equal to 1. And so for the sake of this example, this would be our starting point, a function f of x, which is defined for x greater than or equal to 4. In other words, the numbers greater than or equal to 4 are the domain, and for which the y values are all greater than or equal to 1. And so, as such, that would be this function's range. Then if we were asked to state this function's inverse function's domain and range, in other words, we could be asked domain and range of inverse f of x, then thanks to this rule, we could state that the domain of inverse f of x would be all real numbers greater than or equal to 1. So we would say x greater than or equal to 1, and its range would be all real numbers greater than or equal to 4. So that would be y greater than or equal to 4. And so notice here that the domain and the range have been swapped. And if you're curious to know what this function's inverse function would look like, go ahead and try and follow the two-step method we saw earlier on to find it. And in doing so, upon simplification, you should find that this function's inverse function is equal to x minus 1 squared plus 4, which you could also write as x squared minus 2x plus 5. In fact, do give that a try. Starting from this function, follow these two steps to try and show that the inverse function is indeed equal to this. And as we just said, this inverse function's domain would be all real numbers greater than or equal to 1, and its range would be all real numbers greater than or equal to 4. And there we have it. Now I'm quite aware that that was a lot to take in one single video, and so on the next few videos on inverse functions, we'll be spending time on one specific task at a time. All that being said, that's it for this tutorial.